Okay, so the derivative is a function itself and it has properties. Here is a demo. I have, so here's an example from yesterday. F at x equals, I think it was x squared minus 4x that we did, and f prime at x equals 2x minus 4. Can't remember if that's exactly it, but that's correct. So I could just think of this function, I might even rename it as like, I could call it g at x. It's just some other function on its own. The original function was quadratic. The derivative function is linear. And like, that's just a line that has a line that you probably saw studied at some point in grade 9. Does that make sense? We get that? Okay, so here is our little applet. This is the original function. This is the graph of the original function. You can see the equations of the functions over here if you want to. So the top one is f at x, and it is x squared. And the bottom one is g at x. And in GeoGebra, you literally type derivative f, and it'll calculate it for you, which is cool. And so that's graphed down here. When I drag this point, it moves the other point. Do you see that? So they're connected, and they're directly on top of each other. The y value of this point. Careful. Okay, the y value of this point is what? Nope.
The rate at which f at x is increasing or decreasing?
What's a more common way of saying that? It's the slope of this line, this tangent line, at that point. So this has a y value of just over 2. So the slope of this line would be just over 2. Or if I made it exact, how about I do a bit of a better job and kind of make it exact, right about there. Now this has a y value of 2. And so this line, which is a tangent to the original function at that point, has a slope of 2. What do you notice as I go from here, and then I come around here, and then I go there? There is a connection between the derivative and the original function, and we can say it with sort of natural language and then nice math language, okay? And there's lots of different ways you can think about it, but I'm going to do this a couple more times, and I just want you to watch. Thinking about the properties of both functions when they share the same x value. Okay, what do you think? Maha, you had your hand up?
When the y value for the derivative function is negative, the slope of the tangent for the original function is negative?
Very good. Very good.
Is it that the turning point of the original function is where the slope of tangency is actually 0, or 0 on the g of x?
Yes, you said the slope of the original function, the slope of the tangent to the original function is 0, or at the vertex. The slope of the tangent is 0. But there's more. There's another step to this. What about the derivative function?
When the derivative function passes x, so an x-intercept?
Yes. An x-intercept of the derivative function is where the original function has a turning point, a vertex for a parabola, but some kind of turning point. Because we know that higher degree polynomials can have more turning points, right? So this is a turning point. The slope of the tangent is 0, and the derivative has an x-intercept at that location. Coming back to what Maha was saying, a negative slope tells me what about the original function? If the tangent to the original function, or any function, but in this case the original function, the tangent has a negative slope, then the original function is decreasing. In MHF, we talked about this and we said if you are doing an application question and you get negative 17, you don't say the rate of change is negative 17. You say the height of the ball is decreasing by 17 meters per second. Right? We interpreted that as decreasing. Negative slope as decreasing height of a ball. But we also know that decreasing is a word that we use about functions, whether it's increasing or decreasing. So the y value of the derivative function is negative. At that point, the slope of the tangent is negative, which means the original function is decreasing. X-intercept in the derivative means a turning point. Now the y value of the derivative is positive, and so now I'm in an interval where the original function is increasing and the slope of the tangent is positive. Yes? We get that? Okay, let's look at some other kinds of functions. Here is a, what kind of function is that? You tell me. Sorry. Cubic function. Very good. And the derivative is? Quadratic. Yes? What do we notice about the cubic function? What we were just talking about. What's happening there? Interpret this in terms of what we were just discussing. Can you do that? Check. Woo, except for that one point. So it looks like this cubic function has, the cubic twist is flat, is perfectly flat. The tangent line would be horizontal at that point, right? And you can tell by the derivative because it touches down. Look at 3x squared, x to the cubed, and then this is 3x squared. So it's not shifted up or down. So that vertex is directly on the origin in this case, right? No shifts anywhere, okay? But yes, that parabola, other than its vertex, is always above the x-axis, is always positive. Remember in MHF we talk about whether a function is positive or negative, whether it's above or below the x-axis. We use that to solve inequalities. But now we're thinking about it in terms of derivatives of functions and properties of functions, whether it's positive or negative. Okay, very good. Let's see what we have next. This one always takes a long time to load because it's, I don't know why, but it's the absolute value. So what's happening here? Uh-huh.
There's no turning point, it's just a sharp vertex.
Uh-huh.
So the slope is either decreasing or increasing.
And what else about the slope of an absolute value? Huh?
It is linear. It's already linear.
Yeah, it's constant because that half of it is like a line. It's linear, right? So it's the slope is constant. We don't really we don't do tangents of straight lines. We only do tangents are only to curves. So it doesn't really have a tangent, but you could think of it that way, that it's just constant no matter where it is. And so look at the derivative. The derivative is constant. It has to be. This slope of this half of the absolute value is -1. So the derivative is a constant of -1. Y equals -1. F prime at x equals -1. This is slope of +1 over here. So this is that +1. What do we call what's happening there in the derivative? A break, right? It's jumping from one place to the other. And I'll give you this tip. The function doesn't exist there or there. The derivative function in this case does not exist at, what is that, 3. Does not exist at 3. Think about limits. If the function does not exist at 3,
The limit is up intersection between two.
right, which we can see right here that the limit doesn't exist. And the derivative is a limit. Definition of a derivative is a limit. So the limit doesn't exist. The derivative doesn't exist. That's important. If the limit doesn't exist, the derivative doesn't exist. Okay? And so at a hard turn like that, you are going to have a derivative that does not exist. Something we're going to do moving forward in this course is take lots of derivatives of things. We talked about that yesterday. And we're going to determine at particular points if the derivative exists or not, and sometimes what it's equal to. And if you find a place where the derivative does not exist, turns out that's really important. But this is interesting because the derivative doesn't exist, but the function does. The function does exist there. Okay, and that's a hard corner, not a smooth curve, a hard corner that happens. Because I'm jumping from one slope to another. It's not a smooth transition between two tangent slopes. Okay, what else do we have in store here? Straight line. Uh-oh, it's gone off the page. So what do we notice about straight line? Again, constant slope. So the derivative is a constant. F prime at x equals 2x. Or sorry, f at x equals 2x. F prime x equals 2. The slope of this line is 2. So the derivative is equal to 2. What's this function? Square root. Cool. Okay, square root. We talked about this yesterday. Square root, the slope of the tangent is always positive. And this derivative function is always positive. Square root function doesn't exist over here. What do you see about the derivative function to the left of the y-axis? It's not there. It doesn't exist. But the original function also doesn't exist there. What's happening? Somebody tell me what's happening at x equals 0 in the derivative function. Amnya? We call that a vertical asymptote. Does a function exist at a vertical asymptote? It does not. What causes something to be a vertical asymptote algebraically? From MHF. Not the top. Oh, denominator. Sorry, I thought you said the top. When the denominator is 0, then you have a vertical asymptote. What's the slope of a line with a denominator of 0? Thank you. Undefined. Vertical line. Right? From grade 9, when you have a vertical line, its slope is undefined. So the derivative doesn't exist, but the function does here. What does that mean? This is telling us that the slope of the tangent at that vertex point, or that starting point of the square root, the slope of the tangent would be, No? Well, yeah, sorry. The slope would be undefined and the tangent would be vertical. Just like for a parabola, the tangent at the vertex is horizontal. Same thing here. Okay, good. So this is the irrational function, 1 over x. We talked about this yesterday. This function is always decreasing. Every tangent has a negative slope, decreasing, 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 going left to right. And the derivative function is always negative below the x-axis.
But that one's in the top, like the quadrant one.
So hold on. This is important. This is where we start to confuse ourselves. I think what's being said here is on this side the derivative is decreasing, but on this side the derivative is increasing. But it's the original function that it's decreasing or increasing has to do with whether the derivative function is positive or negative. So we're not asking is the derivative increasing or decreasing. That's not what's important. That actually has some significance, but we're not going to get to that for a while. So this function is decreasing. The derivative is negative. On this side, still decreasing. Derivative still negative. The difference for this one is there's a place here where the derivative doesn't exist and it's a vertical asymptote, but the original function also doesn't exist there. Right?
So let's just say if the original function was increasing, then both the derivative, like both lines would be in the positives, or both of them would be above.
Yeah. I don't know if I can change this. Let me see if I can. There you go. Right? And now this function, their original function, is always increasing. Every slope is positive. And now they're both up. And we talked about this yesterday. Look at it. Look, its derivative is 1 over x squared. Of course that's always going to be positive. How can you make 1 over x squared? What value of x is going to make 1 over x squared negative? None, because I'm going to square it anyway. Okay, we got a couple more. This is a good one. That derivative function looks similar to the one we were just looking at. However, the original function exists. So what's happening here? So I'm increasing. Then the derivative does not exist. Then I'm increasing again. Increasing. Derivative doesn't exist. Increasing again. This is what we call a vertical tangent line. Later in the course, you may want to come back. This is online. You may want to come back and play with it yourself, because there's a couple of very specific cases that algebraically you have to be able to find them. And a vertical tangent line is one of them. So I'm going to compare this, I hope, to the next one that's coming up after this. I don't have the order of these memorized. So this is increasing. Derivative does not exist. And then increasing. Vertical tangent line. Actually, let's do this. Remember the absolute value. It was decreasing. Derivative does not exist. Then increasing. Right? That's a hard point. It has a special name. It's called the cusp. Okay, that's a hard point, a hard turn. When you're decreasing, the derivative doesn't exist, but the function does, and then increasing, that's going to be a hard point. That's what that relationship tells us. Don't worry, we'll go over all this again later. This is increasing. Derivative doesn't exist, but the function does. Increasing again, that's a vertical tangent line. This is another example of a cusp. So decreasing, derivative doesn't exist, function does exist, increasing is a cusp. Algebraically, if you can determine where the derivative function is positive and negative, you can determine whether you have a function that has a cusp or a vertical tangent line or all these different properties of the original function. So that's where we're going in this course. Not in this unit, not today, but in the next unit and moving forward, we start to talk about all of these different cases about when it changes from increasing to decreasing, when it does exist, when it doesn't exist, when the derivative is equal to 0, all of those things. Any questions about this so far? This one's kind of fun to play with because you go ding, 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 ding. Any questions? Is that, like, are people getting that? Do you see that? Do you see the relationship? We'll go into a lot more detail on this. We might even look at this demo again, but just some example of understanding that we're relating the original function to the derivative function. Okay, so let's summarize this. If f prime is positive, f, oh boy, f is increasing. If f prime is negative, f is decreasing. If f prime at x equals 0, f has a tangent slope of 0, and it is likely a turning point. And if f prime at x does not exist, well, there's different things that can happen. Maybe the function doesn't exist. Maybe you have a vertical tangent line. Maybe you have a cusp. There are different things that can happen, which we'll get into more later. Okay, very quickly, I'm not sure you even have to write this down to tell you the truth. Given a polynomial function of degree n, its derivative f prime will also be polynomial. So you don't take the derivative of a polynomial and get a rational function or a square root function. Given a polynomial function, f at x of degree n, f at x is also polynomial and will have degree n minus 1. We kind of saw this happening. So if f at x is cubic, which is degree 3, f prime at x will be? Who understands this or who's lost? Maha? Quadratic, degree 2 quadratic. Good. This is going to become so obvious to you that you don't have to worry too much about it. Okay? If f at x is quadratic, that's degree 2. That's what we mean by n minus 1, by the way. Right? When it says n minus 1, it's 1 less.
Then f prime at x will be linear.
Good. Degree 1 linear. If f at x is linear, that's degree 1. Whoops, I didn't finish that up there above. Degree 1, degree 2. F prime at x will be?
Constant.
Good. Degree 0 constant. Right? We saw that. If f at x is a constant, degree 0, f prime at x will be what? Ibrahim?
0.
Yeah, will be equal to 0. What's the degree of that? Negative 1? No. Degree is undefined, we call that. You don't need to know this. I'm not going to ask these questions on a test, but undefined. Okay? Okay. Now, if you didn't get it written down, you can copy it down after. We have lots to do. I'm skipping example 1 and going to example 2, although it looks like we probably have enough time to come back and do example 1 after, but I want to do example 2 first. For each function, there's only one. I don't know. Yeah, yes, here. This you want to write down, yeah. When you do this, it's also important that these are right on top of each other. Okay? So you want to do this with your ruler to make your two axes so they're directly on top of each other. Do you understand what I just did there? I kept my ruler vertical and in the same place so that they're on top of each other. And then finish your axes like that. I'll give you a minute to get that done. Okay, are we good? How in the world are we going to sketch this? Yes. Somebody taught you well last semester. We got to factor it, right? That's how we sketch polynomials. And then factor again. So tell me something about this. Yep.
So degree 3.
Nice. And?
So x-intercept is 0, 4, and negative 3.
Good. I've got the x-intercepts. And one final thing. Yes, here.
So them are positive.
Yeah, that's not even what I was thinking, but that's right. So we know the order of the x-intercepts. It's got a leading coefficient that's positive. Leading coefficient is positive. Degree 3 tells us about end behavior, like this and like this. Okay, this is going to be my f prime at x on top. And derivative is going to be on bottom. So here we go. I've got positive 3, 0, negative 3, 0, and positive 4. Pass-throughs. Yes?
Does that mean the derivative would be degree 2?
Right? So the derivative, because this is degree 3, the derivative will be degree 2. It'll be a quadratic. And why does that fit? How am I going to know where to draw the quadratic? Anybody?
Is it 12?
What did we just learn about the relationship between the derivative of a function and the original function?
If it's increasing, then it's going to be like the positive.
So this is increasing. This is increasing here. Is that true?
Yeah.
When does it stop increasing? Stop! Right there. Right? That is now not. So what happens when it stops increasing? What happens to the derivative?
It hits 0.
It hits 0. And then f prime will become negative. So crosses the x-axis. So I have to have an x-intercept at that turning point. That's why you want them lined up so that you can. I don't know what that point exactly is. It's not halfway between them necessarily. Okay? And my other one is going to be lined up with the other turning point. Isha, you said the original function is increasing, so the derivative is positive. So I've got to be up here. Then I go negative because my function, look, is decreasing from here to here. Right? Then it's increasing again. So, increasing, positive, decreasing, negative, increasing again, positive. There's your connections.
Do we know where the y-axis is, or do we just
Do we know
the y-axis is it?
no the y-intercept?
Yeah.
No. Not until we do the algebra. We could find it. Everybody got that? For each derivative, there's only one. For the derivative, draw what the original function might look like. So first we have to draw the derivative. Oh, I forgot to label these. Oh no, I didn't. I forgot to label one of them. You might want to label them in case you look back at it after. Just make sure that you know which one's which. Okay, so I'm going to draw the derivative on the bottom and draw the original on top just to be consistent. This one's already factored for us. So this one has x-intercepts of -2, 1, and 3. Oh, I'll give you a minute. You want to do the same thing have your axes, your y-axis lined up perfectly.
Wait, are we gonna do it in algebra?
No.
on cities?
Yeah, you could squeeze it in there. There's nothing special about derivative functions that makes them different in terms of like thinking about their properties. It's just a function. This is a question I could have given you in MHF. You wouldn't have known that it was a derivative of something. It's just a function. And you could sketch it. So don't second guess yourself and be like, well, is it the same for derivatives that like when I'm thinking about end behavior, that it's got a positive leading coefficient and it's degree 3? Yes, of course it's the same. Okay? There's nothing different about graphing a derivative than there is about graphing any other function. So I'm doing the exact same thing. So to graph this derivative, this function, I look at the degree, it's 3. The leading coefficient is positive. If I expanded this, I'd get x cubed. And I have the 3 x-intercepts for this cubic. Okay? So again, this one's going to go like this. It's hard not to make the vertex be right on the y-axis. People do that all the time, but it wouldn't be because this is 1 and this is -2, so it wouldn't be. So I try to draw it not showing that. For some reason, it's hard not to try to put your turning point right on the axis. Not in this case. What would it be? What is it? 6? Yeah. So sure. Good idea. And this is the derivative. Now, what does the original function look like? How many x-intercepts does this derivative have? 2. That tells me this has, well, 3, yes, and 2, what? Turning points. 2 turning points. I'll give you a little tip. It doesn't have to have 3 x-intercepts. It happens to. It wouldn't have to. So if this has 3 x-intercepts, our original function has to have, may or may not have 4 x-intercepts, but you're on the right track. But it has to have 3 turning points. Because when you have an x-intercept of a derivative function, you have a turning point of the original function. So 3 turning points. What kind of a function has 3 turning points and possibly has 4 x-intercepts? Degree 4, which makes sense. Because if you go down a degree when you get to the derivative, you got to go up a degree if you're going the other way, right? So I'm going to have turning points where there's x-intercepts. So I'm going to put 1 here, and and 1 here, and the other one I'm going to put here. So this is at -2, this is at 1, and this is at 3. And this is negative. So my original function must be decreasing. So where do I start if I'm decreasing to a turning point here? Because I'm either doing this or I'm doing this. Which one is it? Check. So I have to be coming down like this. Turning point. Turning point. Turning point. Degree 4. Any questions about that?
Wait, so for this type of question, so every single type of x-intercept we have, we just put a dot there indicating what they're determined for?
Mm-hmm. Most people would have drawn this one below just because and have 4 x-intercepts, but notice I don't. And I could take this function, the original function, I could move it up or down wherever I want, couldn't I? It would still have those same turning points in the same places. It would change the y-intercept and would change the x-intercepts, but it wouldn't change the shape of the function by just moving it up or down. That's actually a big idea in the calculus that occurs after high school, which is interesting. Any other questions?
So would that just be f and x?
This is f of x. Thank you. You really need to think about how the x-intercepts of the derivative are telling us about turning points or maybe other things of the original function. That's what you want to be thinking about. I'm going to do one more thing. I'm just going to sketch it over here. I was talking before about cusps and vertical tangent lines. I think after doing this exercise, this will make more sense. These are 2 original functions. One is not the derivative of the other. Right at this point, what do we call that? A cubic twist. It has a tangent line with a slope of 0. Vertex, tangent line with a slope of 0. The difference between these two, how you could tell them algebraically, is for this one, I'm increasing before, then I'm 0, then I'm increasing again. It has to be a twist. Right? That's what it has to look like if I'm increasing, which the derivative will tell me if I'm increasing. Increasing, 0, increasing, versus decreasing, 0, then increasing. Do you see the difference? I find a point where the derivative is equal to 0. Maybe it's a turning point. I look at whether I'm increasing, I'm changing from increasing to decreasing or decreasing to increasing, or if it's staying the same. Increasing, 0, increasing, or decreasing, 0, decreasing. That's terrible. They don't look like that, that's for sure. And, or decreasing, 0, increasing, increasing, 0, decreasing. Right? If it's changing from one to the other, I know if it's a turning point or if it's a cubic twist. Again, we're going to talk a lot more about this in a couple of units. Not so much the next unit, but more the one after. Okay? Something to think about. Again, you can go back on the demo. I'm going to put this up. I'm not going to do it extra different because it's in vertex form, so the math is a little bit different from some of the other ones we've done together. But I'm going to leave it there. I'll do it and put it up on the classroom, and you can check your answer if you choose to. It's just more practice. It's up to you. I will in a moment. Yeah. Any other questions about this?